Hello, everybody, and welcome to today's Library Maker Talk. My name is Diana Levo-Posner, and I am the Principal Librarian Associate Director for the Exploration and Creativity Department of the Los Angeles Public Library. The Maker Talk program features makers from Los Angeles and beyond who make things. A maker can be a grandma who loves to knit. A maker can be your neighbor who brews beer, makes wine and cheese, and creates beautiful handmade jewelry. A maker can be a barbecue pitmaster, a robotist, a metalsmith, a glassblower, an origami expert, a gardener, a baker, a toy maker, an eco-fashion designer. Makers are inventors, but they don't just invent, they innovate. They hack and repurpose existing or obsolete technology and equipment and knowledge and take away and knowledge and take what we already know and give it a new use and life. So if you or anyone are makers, please email us at ecdept / or at lapl.org. We would love to feature you as our next maker. At the end, I'm going to talk about some upcoming programs we have this coming month on our YouTube and Facebook channel. Most importantly, we have Misty Copeland coming, which is pretty amazing, on February 18th, Friday, February 18th at 4 o'clock. We will be giving some of Misty's book away, Black Ballerina, and I'll talk about it more at the very end. But without further ado, I'm going to bring on the amazing librarian, Vi Ha, who is our senior librarian for international languages, and she's going to be introducing today's makers. Vi?
Hello, thank you so much for that intro, Diane. So prior to being the International Languages Senior Librarian, I was running the Octavia Lab. And the Octavia Lab is a maker space that's available for free for Los Angeles Public Library card users. And with it, you have access to 3D printers, laser cutters, we have a CNC mill, we have a whole bunch of grand suite of software that's available for free for Los Angeles Public Library users. And we are always at the Octavia Lab looking for volunteers and looking for people interested in making and within the community. And that's how we got introduced to Team Curiosity. Hey, Team Curiosity, are you there?
Hi!
So pretty much, can you guys introduce yourselves? And
Yeah, I'm Julianne. I'm one of the co-captains of Curiosity, and where a robotics team participates in something called First Tech Challenge, which is an annual competition for middle and high school students in robotics. And we're going to be doing a little overview of our process of making a robotics and a few robot demonstrations.
Hi, I'm Ezra. I'm the other co-captain on Curiosity, and I've been on the team for 3 years. Hi, I'm Chase. I'm in 11th grade. I work on hardware with the team, and I've been on the team for 3 years.
Hi, I'm Casey. I'm also in 11th grade, and I've also been on the team for 3 years. I work on hardware and outreach coordination.
Hi, I'm Julia. I'm also in 11th grade. I also work on hardware and mechanical stuff, and this is my first year on Team Curiosity, and I'm so excited to be here.
Hi, I'm Melody. I'm in 10th grade. This is my first year on Curiosity, and I've worked on some coding and touch sensor.
Hi, my name is Angelita, and I've also worked on technical and mechanical things. And this is also my 3rd year on Curiosity.
cool, thank you so much. Okay, so you want to talk about your team and your organizations you're a part of? You guys had a slide deck all ready for us. Are you ready to go? Okay,
Yeah.
Let's do it.
All right. So as I said before, we're Team Curiosity. We're a team of women and gender minorities out of Marlborough School in Los Angeles. And our mission is to set an example for aspiring young scientists and engineers while having fun and working together as a team to solve complex problems.
Great. Let me click there. Did that work?
Oh, next slide.
Okay, there we go. All right. So we compete in a competition called First Tech Challenge. It's one of 3 competitions hosted by an organization called FIRST for the inspiration and recognition of science and technology. First Tech Challenge is for middle to high school age students, and it involves teams of around or up to 15 students. So First Tech Challenge every year releases a game that we design a robot to play in. And we play with 4 other teams on a field. And it's a great way for us to build our community, to build our knowledge of STEM, and to really see all of the options that are out there for STEM-minded people like us. So we're going to get into a little bit of our design process here because we think that's, one of the most fun and interesting parts of being a maker. All right.
So for our design process, so in September, the game is released for the year. And so we have to start by examining the game and what kind of actions we want our robot to be able to do in order to do well in the game. So we do a game analysis and we look at all the different things a robot can do, or a robot could do in the game, and we come up with what we want our strategy to be. So what do we want our robot to be able to do? And so that leads us to our functional requirements. So functional requirements are really not thinking about what your robot is going to look like, but what it is going to be able to do. And so that way you can design your robot with its functionality in mind. So after we kind of come up with a list of things we want it to do, say drive across the field for a starter, or be able to pick up a block or place a block at a certain height, or do any of the kind of game tasks that are in that game. We go into brainstorming what kind of mechanisms could accomplish those functional requirements. So as a team, we do like a rapid kind of brainstorming session where we draw or sketch out really simple designs for all different kinds of mechanisms, and then we group them by kind of what is similar, what different kinds of mechanisms, and then we kind of come up with what our different subsystems of our robot are going to be.
So our team spends a lot of time in the brainstorming process before you even start fabricating or even prototyping these mechanisms. So one of the things that we do is after we have the different subgroups or parts of the robot that we want to focus on, we make something called what's it called? A C-sketch. So we're essentially splitting a paper into 3 different parts, and we put our top 3 mechanisms on there. And those we want to make as different as possible so we can think about all the ideas that could potentially work to solve the problem that we're looking at. So we have 2 examples of C-sketches, and we can just take a look at the placing one. So we have 3 different mechanisms. We have lifts as slides, and then we have both a horizontal and a vertical conveyor. So after we sketched those, everyone in the robotics team went around and they put their comments or questions or concerns on these. So it's a very collaborative process, and we're able to really narrow down our ideas with the input of everyone on the team.
After taking note of everyone's ideas on C-sketches, we then move on to creating prototypes of our 3 ideas. So I'll be talking a little bit about our intake prototypes, which are on the left. So as you see here, we have 3 different designs, which we use to test, which is going to give us the fastest speed time for when we're intaking things called freight, which we'll talk about later when we explain the game that we're playing in. And so what we do is we take each of our 3 prototypes and test them to see which is going to work fastest and what will be the most efficient for us to use in game.
Part of our prototyping process does involve some more custom fabrication of parts, because each of our parts on our robot we make using 3D printer and laser cutter, which allows us to have a lot of flexibility in our design. Can we stop sharing the screen for a sec? Can we unshare the slideshow? Yeah.
Perfect, thank you.
Thank you. So once we have a sort of idea of what we want our robot to do and the different mechanisms and what they are, we'll use something called computer-aided design, which allows us to build a model of different parts on the computer, and then we can use our 3D printers and laser cutter to fabricate them. So this is an example of a piece that we laser cut. So we essentially have a line drawing of this piece, and then we transfer this into the laser cutting program, and the laser cutter will carve out all of these holes in a very specific way, which allows us to have a lot of flexibility in our design since we can make those very specific parts. And then we can fabricate things out of wood, and we can also use acrylic, which is a sleeker look and is also good for things like gears on the end because they can mesh together really well with the acrylic. And with our 3D printer, we can print parts that have more dimensions. So the 3D printer model is more complex and has more aspects to it. So this is an example of a part printed with a material called PLA, which is a very rigid material and can hold up strong parts. But we can also use something called TPU, which creates a flexible filament. So when after it prints, you can actually bend the part. And this is a part that we now have on our robot for our intake because it allows us to flexibly grab different materials of different sizes and shapes, which makes it really easy to actually grab the parts off the field. So it's really cool that we have this flexibility within our design to both laser cut parts out of different materials and also 3D print parts that have different physical characteristics.
Another really important part of the collaborative design process is the fact that when we start to fabricate parts using the 3D printer or the laser cutter, there are many different iterations that go into creating a robot. So one example we have here is our team element, which is a very important part of scoring points in the game. And we'll go into more detail about why the team element is so important later when we describe the game and overall process. So basically, when we first started out the season, we wanted a bigger team element. As you can see, it's a little bit block top heavy and it's not very functional. So as we went through the season and we went through playing matches and participating in different games and collaborating and deciding on what the best process would be, we ended up with a smaller team element that's much less top heavy and actually ends up doing the job really, really well. So yeah, another great example of everyone.
I have a question. What is it made out of? The team element.
Of plastic filament.
So it's 3D printed.
3D printed.
Yeah, 3D printed.
And the lines that you see on are actually gap tape, which help us in game, so we're actually able to scan the team element, which we'll be showing you later.
Yeah. So the team element design process is also just a great way to showcase that there is so much range in what we're able to 3D print. We have pieces that are tiny, this is a belt grip that we use on our linear slide system. And we also have much larger pieces. I think this one is probably 7 inches tall, just to make sure to clarify that there are so few limits to what we can make with these tools, and we're so grateful to be able to have access to them. So next, we're going to showcase one of our mechanisms from last year. So as Chase was describing earlier, we brainstorm each part and fulfill each functional requirement of our robot in separate mechanisms. So one of these separate mechanisms from last year is our launching system. The robot does not currently have wheels on it, so we can't drive it for you, but we can show you what launching a ring would look like. Launching rings was part of last year's game, and yeah, we're super excited to show you. Here, I will step aside here.
Cool.
So can you bring the camera closer?
Yes, and I can bring the mic too. Here, you can unplug it.
Okay. So this is our robot from last year. It's mostly the intake right now and the shooter. So last year we had to score these rings in a goal. So as you can see in a second, our robot can pick up these rings from the ground and it brings them up into a sort of holder up here. And then once we start the shooter, it's really loud. It can launch them really high and really fast, which allowed us to score a lot of points last season. So this robot is sort of the final iteration of a lot of different changes. Originally, our shooter, didn't work very well. That's part of a process of robotics, is that we get to go through a bunch of redesigns and come up to a final product that works really, really well. So this is an example of just our robot from last year, and sort of all the thing that it's mostly capable of is launching these rings.
One more thing I want to add, about last year's robot, was last year, because of the pandemic, modularity was really, really key for us. So fulfilling the functional requirements and the mechanisms that were described earlier, each of the, here, I'm actually going to turn the camera back around. Each of the mechanisms on this robot are completely removable from each other. This intake at one point, and I think still can, be removed with 8 screws. This really allows for us to iterate each separate mechanism and makes it easier for us to make fast iterations. If something doesn't work, we can change it immediately.
Okay.
And it really allows for a great, fast and speedy design process.
Okay, I have a question then. So how many? So this robot here, it looks like it can pick up something, and then it can move something to a certain height, right? And then from that, it can then both. Is there any aiming, or is there the only game was to actually launch it as fast as you can and as far as you can?
So there was a target that we had to hit. Initially, we just aimed by rotating the robot. Unfortunately, our wheels are no longer on the robot because we had to reuse the wheels for a robot for this season. But we are in our game, we were able to sort of aim at those targets, and we also used encoders, which are sort of trackers on the motors, to get the wheel that launches the rings to a very precise speed, and this allowed us to hit the targets very consistently because we could vary the speed depending on which target we were aiming at.
And then something
Okay.
I'd also like that every year the game changes. So last year it was focused on shooting these types of rings at what was called a power shot, and so that required us to readjust our robot and how we were positioning it. Whereas this year we're focusing more on picking up items and placing them into designated carriers, which we'll explain about more about later.
Yeah.
Thank you.
Explaining the game.
Yeah. All right. So with that, we are going to get into explaining our game a little bit more. So our game this year is called Freight Frenzy. And got it. Can we put our slideshow back up really quick? Thank you. Awesome. All right. Okay. So our game this year is called Freight Frenzy. Every year, FIRST and FTC, as part of FIRST, releases this game for us to play in. And most years, it's designed after something practical in the STEM world. This year's game is supposed to model what shipping looks like. So we have elements on the field called the warehouse. It's a large corner of the field where freight, or boxes and balls, are stored at the start of the game. We also have places called shipping hubs and storage units. So even though we can't really get a sense of what, the shipping world is like out there, this game allows us to become familiar with the terminology. It encourages us to research a little bit more and to really see what kinds of futures we could pursue. This year's field, I'm going to go over, features, or the game elements this year have cubes and balls. Some of the cubes are heavier than others, just to make it so that lifting is a little bit more challenging. Some basic field parts or sections I'm going to describe here. We have the warehouse that you can see up in the top corners, the shared shipping hub, which is in the center, and that both teams will move freight from the warehouse onto, and then alliance shipping hubs that each robot will try and collect freight. Each robot will try and collect freight from the warehouse and place it in a shipping hub, either the shared one or the alliance one. Alliances, do you want to explain alliances?
So there's 4 teams. 2 of them will be on the red alliance and 2 of them will be on the blue alliance. So for the alliance shipping hub, if you're on the red alliance, then you place on the red alliance shipping hub, and you shouldn't interfere with the alliance's shipping hub. And then you can also store freight in the shared shipping hub, but you can't move it.
And a little bit more about alliances. Alliances are actually chosen at each meet randomly. And so we'll be paired up with different teams from other schools or from the same school that are within your league. And then you'll get the chance to work with them as an alliance, and we'll possibly play against them in the next round, which makes FIRST competitions really unique in the way that the person that you could be partnered with could be the opposing alliance in the next game.
All right, so we are going to go out to the field and show you our robot and how it works. We're going to do a little game demonstration for you. But first, we want to show you here what our robot looks like. We have a full CAD, or computer-aided design, model of our robot. Every year, we CAD a full robot with all of its mechanisms. It really helps us make sure that everything is going to work together. One of the coolest things about this team is that everyone on it knows how to CAD. Does someone want to go into the CAD process a little more?
Oh, sure. So in order to make our custom fabricated parts, we use computer-aided design software. And so we use a site called Onshape, which allows us to work collaboratively on different parts. And so when we need to fabricate a specific part or a design, we'll use that software to be able to create it and then export it as a file to 3D print it or to laser cut it.
Using Onshape also allows us to kind of organize our ideas and make sure that all of the mechanisms that we've created individually will actually function together and create a robot that really works well and that will actually, come together in the real world. So it gives us a way to kind of test our ideas and see how they'll work before we actually spend the time fabricating them in real life. And I think we can do a quick introduction of our robot, just a few basic mechanisms on it before you see it in action in a game on the field. So as you can see on the picture on the left, that is our CAD design. And we've just pointed out some of the main aspects of the robot. We can start with the lift. So we use Masumi slides to create a cascade lift, which can extend to about 1.5 feet.
Yeah.
So yeah, that is a very important aspect because that's how we take the freight and we move it to the different levels of this shipping hub, which we'll see in a second. Another important aspect is the claw. Our claw actually has 3 degrees of rotation, and we use servos to be able to manipulate that claw and move it. So that's how we grab the team scoring hub and the different freight and score them. So our drivetrain is actually made with mecanum wheels, which allow us to both go forward and backward and then side to side. So we have a lot of flexibility when we're moving around the field, which makes it a lot easier to get to where we want. All right.
Our intake brings in the freight, and it incorporates what Julianne showed us earlier, these 3D printed, flexible, I'm not quite sure what to call them. Flippers, we'll say, that can sweep up the freight and bring them onto a ramp that goes into the body of our robot. The ramp is really special. It's part of our whole driver-friendly design process. We want to make everything as easy as possible for the drivers, and that means that we automate things, we have scanning mechanisms, and one of these big things this year is our ramp. Our ramp moves up and down. So one of the big pieces of the field that I think I forgot to mention is barriers. There are barriers on the field between the warehouse and the shipping hubs. And so we have to either drive between them, which we can do as we've specially designed a small drivetrain this year, or over them, which is definitely the faster and more efficient way to do things. This ramp moves up and down with the starting of the intake. So when the ramp goes up, we can drive over the barriers and the ramp won't be affected by the barriers, which are, I would say, 1.5 inches tall. Just to give you some context, they are kind of large. And then one other thing to mention here would be our claw. We talked about the claw. Yep, duck spinner. There we go. So I'm not quite sure, actually, what part of the shipping world the duck spinner incorporates. It might just be for fun. But there are Lazy Susan type devices on the corners of the field, down on the bottom that you can see, that are called carousels. And we have rubber ducks, which are quite cute. And the rubber ducks are placed on the carousels at the very end of the game. The robot will spin the carousel and make the duck roll around and fall off. And each duck landed on the field scores us a certain amount of points. Yes. Cool. All right, so we are going to take us out to the field now. And there we can talk a little bit more about our coding process, and in general, we can talk and we can really demonstrate for you how our robot is working this year.
Okay.
Awesome.
So with this map here, like what you have, which I see, are you guys also building a model of this playing field also?
Yeah. The model is sent to us, actually. The model of the field is sent to us by First. And it's quite large. I forgot to add, it's a 16 by 16 foot field. So if I turn this camera around here, you can see it's kind of large.
So you can see Ezra's on the other side of the field.
Yeah,
One
so
moment.
Ezra's on the field.
Steve, can you stop the screen share for a second?
Yeah, that'd be great.
Yeah, we'll talk about that in a second. All right, so
Not yet.
we're going to explain a little bit about the gameplay before we start.
Thank you.
Thank you. So as you can see, this is our field, and our robot's on the other side. So we're going to bring this closer.
Okay, this is our general field setup, and we're going to pass over to Ezra for further explanation.
Hi, so this is our robot from this year, and we're going to explain a little bit about how it functions, so you can kind of understand the gameplay. So basically,
I want to intake stuff.
All right, great. So I'm going to explain really quick from behind the camera here what this setup is. Right now we are against the wall of the field, which is where the robot would start in a match. At the beginning of a match, there is something called the autonomous period. The autonomous period is a period where the robot moves entirely on its own, pre-coded by our wonderful coding team, and we are able to sense and detect this team scoring element that we were discussing earlier, and then pick up freight and place it at a different tier of our shipping. And after auto, we move into something called teleop, which Melody is going to explain now.
So teleop is the period where the drivers pick up the controllers and they start moving the robot on their own. So autonomous is the coded part, and then the type of score freight at 5. Moving the robot, there are 2 drivers, driver A and B. So driver A would maneuver the robot, and then driver B would be the one that intakes and places freight. Our robot
Can't hear
has
you.
a lot
Melody
of-
can't hear you. Speak louder.
Our robot has a lot of cool functions like a touch sensor and distance sensors that allow the drivers to know when freight is being intaked and at what points that they should be placing freight. Let's go over
Yeah, so we're going to go over how our robot in this season works. So we have to pick up these pieces, these little blocks, which are called freight. So to do that, we have this intake in the front.
So like Casey was talking about earlier, we have a ramp, and so that is this thing right here, and so it lowers when we want to intake, and then it goes back up when the intake is not ready. So you can see it automatically goes down, and then we can intake freight, and they go into the claw, which is right here, and
So I think we were going to do a little just overview of what it looks like when we're actually playing the match with teleop and what it looks like to score in the different tiers. So keep it so you can see the field.
Yeah. All right, I'm going to bring the camera back a little bit so that we can see the full field here, or the full half of the field. We only work on half of the field, really, for the game. The field is divided, as we showed earlier, into the red and blue sides. And right now we're just demonstrating on the red side because our team color is red and we think it's fun. But all right, so there we have our claw and lift at work. Our lift, which is rigged with a small conveyor belt, or a small belt, is fully extended, reaching up to the 3rd tier of our Alliance shipping hub. And you can see in the hand of the claw, which is on top of the lift, we have our freight.
yeah, so this is yes. So here we have our lift, like Casey was talking about, which has lifted the claw up to score in this top height of the shipping hub, and then in our claw we have a piece of freight. So when I release the claw, it'll drop in here, and so we scored a piece of freight. So that is good. And then we can retract the claw back in, so it just flip into the robot, and then we can lower the lift like that.
And once, after we score one piece of freight, we have to go into the warehouse, which is this back part of the field here, and intake another piece of freight.
So you score points by picking up freight, and do you score points from where you put? Like I see there are 3 tiers.
Yes. So we score freight by putting them in one of these 3 tiers. So the top tier is the most points, so that's generally where we aim for. So that's one way we score points.
And so one of the main tasks of the game is to grab freight from the warehouse and deliver them to 2 different shipping hubs. One being the 3-tier shipping hub you see over here. We could change. and the other one being a shared shipping hub in the back area. And so one of the interesting parts of the game is that where the two opposing alliances get to interact is actually through this shared shipping hub, which robots from both teams place prey on. And so because these are actually wobbly, we're able to tip them over. So if we tilt this camera down, we can see that by putting a heavy block, which you can see here as Casey explained earlier, will allow us to tip over the shared shipping hub in our favor. And so tipping it towards your alliance allows you to gain more points during teleop. And so the opposing team can put blocks on their side, and then see now it's balanced. And so you want to try to keep putting more and more in your side to balance it in your favor. And so adding in a little bit more about auto, teleop, and endgame, there are different tasks that allows you to gain different amounts of points depending on what task to complete. So for teleop and endgame, something you can do is adding freight to the shared shipping hub and to the line shipping hub. And for auto, there's various amounts of tasks we can do, including scanning the barcode, which includes scanning the TSC, which we mentioned earlier with our camera on our robot over here. And so all of this is pre-coded by our wonderful team, which Melody can explain a little bit more about the auto process.
So in the autonomous, the thing called the barcode is, you put the camera up so we can see this. So the barcode are these 3 red squares, and at the beginning of each match, there will be a randomized position to put the team element. So the team element can be in one of these 3 positions, and each of those positions corresponds to a different level on the shipping hub. So for example, when the team shipping element is placed on the middle position of the barcode, that means we have to score in the middle position of the tier. So we're going to demonstrate our autonomous, where the robot makes that decision on its own. It's pre-programmed to identify where the team element is, and then it places it in the correct place.
So how the robot is able to do that is it has this camera right here, and so this can see the 3 positions, and it can identify on its own the team element because it knows what the team element looks like because we've trained our camera and the algorithm to know that, and it can identify which of the 3 positions it's in and then make its own decision based off of that. So we're going to demonstrate that right now.
Back up so you can see in that side.
Can you narrate as we go?
Yeah, all right. So right now, Julianne is starting the robot. And I think there we go. All right.
It was one line up correctly.
All right. We're going to be completely honest with you right here. The robot did not exactly sense the right
Oh,
element.
it's stopped. It's because the battery, like it disconnected. That's why.
All right. It looks like we have a bad battery on the robot right now.
Ooh.
Okay.
That's okay. I have lots of questions about your robot already. So.
Oh yeah, we'd love to answer them.
Okay, so I have question number 1. It's what programming language are you using, or what's your chipset that's running all this? It's like I know how to use a laser cutter. Oh wait, we should probably talk about how to use the laser cutter and how to use all that. But let's start with the number 1. What programming, what chipset are you using on this thing?
Yeah, so I'm going to pass the microphone to Katie. She's on our coding team, and she worked on the autonomous this season.
Sounds
Hi. So that's a really great question. We use Java, which is used in a lot of stuff, including Minecraft, if anyone's played that. And we connect to the, it's called a control hub, which has its own Wi-Fi with our computer. And we can do it just like using Wi-Fi connection, and any change we make, it just connects, and then within 15-20 seconds the changes are uploaded to the robot.
So specifically for the autonomous zone, you're giving it a bunch of if-then statements. If it's here, do that. If it's that, do that. If it's that, do that. Is there programming that goes on with the non-autonomous section? I forget what it's called.
Yeah, so it's called the teleop, and during the teleop we have a robot. Could you bring the robot controller over here? We have a robot controller, and every button has a different purpose. So on here we have to be able to tell. We have to be able to tell the robot that if you press this one or this one, if you go this direction, whatever, or if you press any of the buttons, to open the claw, to raise the lift. And we actually have some interesting things with a touch sensor on our robot as well, in the teleop, which also uses some if then else statements.
Cool. So how long? Okay. So basically, so there's two sets of instructions. There's many instructions that go on. Is there, and then how long did it take you to learn Java, or did you sketch it out in English first and then code it, or is there pre-made code that you guys can work with?
There's a lot of great code online, like to help teams get started. There's sample code, like on the internet, and the FTC community is really great. Me personally, I started learning Java like a few years ago, and I use that knowledge to help me now. But a lot of what we do starts with a code template. And then what was the other question? Sorry.
It's basically like basically you answered my question. It's basically you're using that's a lot of stuff that's pre-made, and you're just using the design elements, what you're trying to do, and making that fit in that way. Yeah, I got it. Cool.
Yeah.
Does everybody know how to code, or is it just there's a part of the team that does the coding, or is
A majority of the team knows how to code, but not everyone. But we try and teach everyone that comes onto the team some basic coding foundations. But do you want to talk about?
Sure. So I worked a little bit on sensors, and so if you do go on like the Rev website, when you look at the sensors, there is some like test code that you can look at. We actually this year are using a color sensor that has distance sensing properties in order to sense if a piece of freight is like in the claw or not, and then turn an LED light a different color if there is a piece of freight, so that way the drivers don't have to like look around and see if they can see if the freight is inside, and it makes their driving experience a little easier. So me and a few of my teammates that are a little newer to the team did find that code online, and then we were able to like learn about the distance sensing part, and then use some previous coding knowledge and some help from the other autonomous coders to program that.
cool? So I have a question about the general building. Oh wait, do you guys have more to the show before I start asking 20 million questions?
Yeah, so we're going to show our autonomous van now with a working battery. We also should use it here out of the
Okay.
So, to cue on this, we're going to show it in the third position. Is this or second position? Okay. Yeah. All right. So, Angelita's going to start the autonomous, and what it should do is scan the placement of the team element and place it in the correct tier of the shipping hub. That we have one there. Red camera. Did you start? Okay. So first we have to make sure that it initializes, which means that the robot sort of gets all the information that it needs, and then it'll it'll tell us in the code that it's ready to be initialized, which means that it's ready to run. So once it does that, it can run it. We have a bit of a delay built into our program because that helps us avoid collisions with other robots on the field. So once that delay is over, it will move and score in the correct tier. And then once that's done, another part of the autonomous is the jump spinner, which it lines up to the carousel. And then it parks in this box here.
Awesome. Thank you. You got it to work. Okay.
Yeah, so that's the first 30 seconds of the game, and then the next 2 minutes of that game would be under driver control. So you notice in that 30 seconds, you're not allowed to touch the controllers at all, and it's all the robot doing it on its own. Yeah.
Fantastic. Yeah, I like your wheels that you can both go sideways and forwards with the same set of wheels. How does that wheel set work? Can you flip? Is it okay to flip the robot over to see this?
So these are called mecanum wheels, and essentially these wheels have rollers on them. And these rollers allow the robot to do the sideways motion. So when all four wheels go forward, the robot moves forward. When all four go backwards, it moves backwards. But then these wheels, they can also turn inwards towards each other, and that allows it to go one or the other direction. So when some of them are turning like inwards towards each other, it goes one way, and then when they turn out from each other. On the other side, they go the other way. And so here's an example of that wheel off the robot, and you can sort of see how it's the shape of a wheel, but has these diagonal rollers, and that allows it to slide along the floor in this diagonal way, so that when it's turning, it can actually slide directly horizontally, which makes it really easy to maneuver around the field. Since we don't have to turn to a precise place, we can just line our robot off with the same heading and go left and right and forwards and backwards.
So it's always in 90-degree angles then. It's not possible to do 45.
Well, we can turn it normally, and we do, but it's nice to be able to have that flexibility with the wheelbase to be able to go left and right in what we call strafing.
And if we wanted to like move diagonally for some reason, then we could like say because if we do motors at different powers,
Yeah.
it'll go diagonally basically. Yeah, because when they're all the same power, it'll go side to side, and so if you make one more or less, then it will go diagonally.
Okay, so what percentage of this stuff was made in your makerspace? I'm assuming the laser cut pieces are.
So
Go ahead.
I can put this back over. So you can see we have these 4 main wood panels, which kind of make the structure of our robot, and these are all custom fabricated. So we design these in CAD and we cut them on our laser cutter. And then you can see we have these fingers, which are 3D printed. We have the claw. So these wood pieces are all laser cut, and then these claw pieces here are laser cut in acrylic. So acrylic is really good because the gears can be really precise and mesh really well and be strong and not deteriorate the way wood might. So that's our claw. And then we have this battery holder is 3D printed. This is 3D printed.
And the lift has a lot of different 3D printed parts because we wanted to make sure that, so our lift works with these belts connect to each stage of the lift, and they go through pulleys. So we have these custom 3D printed parts that hold the belt in place and also hold the pulley in place, and that allows the lift to move up really easily. So the only parts of our robot that we didn't make are pretty much the metal parts. So for example, the linear slides on the lift are parts that we didn't make, and like the motors and wheels, but most of the main like components of the robot that actually move and the Mac are things that we made by putting different pieces together.
Okay, so for the metal parts, like for example the lift right there, did you have to cut that piece to size, or did you buy it, or did you Frankenstein for another robot?
All right, so a lot of these pieces are actually Frankenstein from other robots. Like we mentioned on the robot that we showed earlier with the launcher, those wheels were taken off to be used on this one. These slides we had used in a game 2 years ago. But between these slides here, we have channels, and the channels were not Frankenstein, actually. So these channels that we have here, we buy in long, like strips of them. And in our robotics lab, we have all of these really fun power tools that we get to use to cut them to the specific sizes that we would like them to be.
Okay. So go ahead.
There's also so on the bottom of the robot, you can see we have these metal channels are parts that we purchased from a part supplier, but we also wanted to make some customizations to them. So for example, there's this notch here because it allows the servo from the claw to not hit it, and we need that notch there so that we don't hit the servo along there. So we used a cutoff wheel, a Dremel tool, to cut a notch in this. So while we can have some flexibility with those metal parts, having the wood on our robot does make it a lot easier to do that customizability, and ultimately results in a robot where we can change the design of it a lot.
Cool. Yeah, so pretty much you guys, you're familiar now through this robotics program with Java, programming in Java. You're now familiar with CAD software, both with actually drawing 2D and also 3D. You're also familiar with actual building a prototype in your CAD software and seeing it kind of test out. And then from there, you're able to take these parts, but you still have to know that how did you figure out the tool? I know that's in your early design process, you had like that little C sketch where you have like potential solutions to these problems. How did you decide which solution was the way to go?
Yeah, so we are going to go back inside and we can show you the full robot sketch that we have up. The way that we really assess these pieces is assess our mechanism designs is through a lot of extensive prototyping, like we showed. And like you kind of mentioned earlier, we can Frankenstein from other robots. So one of the claw prototypes that we used this year was the same claw that we had used 2 years prior. And we decided that we wanted to build a similar mechanism, but we customized it a little bit more to the balls that we were using in this game. I'm going to pull us over here behind us. One of the great things about our space is these big rolling whiteboards. And this one here has our full robot sketch on it. So to make sure that all of these pieces are going to work and fit together, we draw them out in 3 different angles. We color code them. We allot for space. And then that's when we really take it into CAD to fit everything into one piece.
Yeah, so these drawings show the top view, the front view, and the side view of our robot. And these are really helpful for determining the shape of the panels and exactly where mechanisms go. And these are rubbing off of it because they're a few months old now, but you can see how this top view of the robot really matches how we actually ended up designing our robot. So you can see that, you bring the camera over, the claw positioning is fairly accurate to where it is in the drawing. So going from those drawings to CAD really allows us to make a robot that has a deterministic design where we determine what we want our robot to be able to do and then design it based off of those requirements rather than making a robot and then trying to fit requirements into it. We really make a robot with specific design parameters and functional requirements in mind.
And in terms of like how we pick specific things, I can speak a little bit about the ducky spinner, which is basically just a wheel with a motor. So we align by a principle called the KISS principle, which is just keep it super simple. So instead of like trying to make things super abstract, if possible, we try and keep it simple. And you can see this also in our intake. Like there's a lot of ways to make this a bit more complex. Maybe we would have had like, I don't know, like a ton of rollers or a second layer. And those maybe could work better in certain circumstances, but aligning with this principle, since this works, it's like easier to update and repair and everything. If we try and keep it like, this works, let's go for it and then go from there.
Well, this works with as many of the objects as possible. So you had mostly cube objects. I didn't see any round objects or objects that change shape. So this, yeah, agree.
We actually, once we started playing the game, we sort of decided that the cube objects are a little bit better because they don't move around as much. So especially when you're scoring in the shared shipping hub, it's better to have the cubes because they're heavier. And in the Alliance shipping hub, while the balls might be lighter, it's still nice to have ones that won't like move around there because that can mess up your scoring if you have something that's like rolling all over the place in the scoring tier. So it kind of makes it easy for us to determine if we actually have a piece and to be able to score it consistently if it's only the cubes.
In addition, on each field, we have 28 cubes on each side, and there's only 10 spheres, which means that we have more opportunities to score the cubes rather than the balls.
Yeah.
Cool.
All right, take us back here. Let's see, how much time do we have? Ooh. All right, so it looks like we are
right around 7 minutes still. Yeah, you guys did great on time.
Awesome.
So, Diane, so there's a question from the audience. This has been very inspiring. What are Team Curiosity plans for the future? What universities do you hope to attend? And do you want to continue to be makers? Any of you guys, let's do it.
Yeah, so none of us exactly know where we're going to school, but I know that a lot of us, I myself want to go into engineering. I want to study mechanical engineering, with applications to space exploration, because that's something that's always interested me. But the nice thing about robotics is that it brings together a group of people with a lot of diverse interests that range from, like, everyone has some interest in STEM for robotics, but that can be applicable in a lot of different ways.
Sure. For example, not all of us really align with classic STEM principles of being really into math and science. And so, as someone who's also more interested in the humanities and is very much interested in environmental science and environmental material science, and so being able to work in a team environment and being able to solve problems, and we can use the skills that we've learned from problem solving and the collaborative design process into the real world. And so I think we're all really grateful for the skills that we've acquired and are so excited to become real world problem solvers and engineers for any kind of field that we want to go into.
One more great thing about FIRST and about FTC and really the team environment is that we aren't only developing tech skills, we're developing skills like mentoring and marketing. We're developing social media, how to build a social media presence, how to communicate with peers and with adults, like setting up this makers talk that we are doing right now. So different aspects of our team or different sections of our team will focus on different things, but everyone on our team generally works together on all processes, and so we all get exposure to all kinds of great skills here.
And I think just a great part about participating in robotics and STEM in general, even if that's not something that you want to study, is that you really learn the importance of problem solving and communication skills. So I started on Curiosity when I was in 7th grade 6 years ago, and I wasn't very good at communicating ideas effectively. But then after being on the team for 6 years, I really learned how to explain complex solutions and complex problems in a way that my teammates can understand, and also share the knowledge that I've acquired with my teammates for something that might be hard to learn, like CAD. And it's just really amazing to see how everybody can sort of use those skills to solve problems, because once you learn how to solve those problems and you're given the tools to do that, you can then apply that into other aspects of your life.
So just in general, one more time, or not one more time, just in general, what Team Curiosity is looking forward to this season. Coming up next weekend, we have our regional qualifying event, where we will be competing in games, in matches. There we go, in matches, like the one that we demonstrated for you earlier. Hoping that we qualify for regional competitions. We have those in a couple of weeks, and Curiosity is really looking to go to Worlds this year. We have qualified for the past 2 years, and both times we were not able to go due to COVID. So we are really, really pushing for that this year. And yeah.
Well, we here are looking forward to seeing you guys compete at Worlds. I mean, if not that my word has anything to say with it other than positive intent and team building. I really makes me feel very good inside that you guys value problem solving and communications, because those are definitely really the next generation of, like, if you want to solve a problem, you want to do good in this world, those are your two biggest skill sets. Thank you so much, Team Curiosity. Diane, you ready to pop back in? Or do you got another question on there that we want to ask the audience? Or from the audience?
Now I'm ready. Oh my God, you guys are so inspiring. Yay! Go World! I hope you guys get in. We'll be cheering for you in the library. And yeah, thanks, Fee, for being able to connect with Team Curiosity. It's just going to be amazing. You can catch this. We're recording the whole thing, and you are on our official Maker Talk playlist. So, feel free to put that on your college apps. And hope to see, maybe we can reconnect again when you guys win World.
Yeah, thank you so much.
Thank you so much.
Thank you.
All right. Wow, V. I mean, that was just amazing. I'm so inspired. And, I just, hopefully all of you, if you're interested in being on our Maker Talks, you will email us at ecdept@lapl.org. We'd love to inspire some more people with all the makers out there. And don't forget to check out our next LA Made program, which is tomorrow, Thursday, February 10th at 4 p.m. We will be welcoming Ron Parker to the LA Made stage for the History of Black Dance in America Part 2. It will be a Zoom program, so you can email us and we can send you the Zoom link. And this Friday, February 18th, we will virtually be hosting Misty Copeland, the first Black woman promoted to the principal dancer of the American Ballet Theater Company. And she will be discussing her book, Black Ballerina, My Journey to Our Legacy. And we will be giving away, sending people copies of her amazing and beautiful book. So hopefully you'll tune in. This program is also will be recorded, so you can check it out on the weekend if you're not able to attend on Friday at 4. Thanks so much again to Viha and to the Team Curiosity team. And remember to check out all our other amazing library programs at lapl.org/events. We'll see you next time. Thank you.